The AI-assisted generation of difficult math questions paper introduces a novel approach to automatically generating challenging math problems, leveraging recent advances in artificial intelligence and machine learning. The authors, Vedant Shah et al., aim to address the limitations of existing math question generation systems, which often produce simplistic or uninteresting problems. Human-generated questions are time-consuming and expensive to produce, while automated systems struggle to create problems that are both challenging and relevant. The authors propose a hybrid approach, combining machine learning and mathematical expertise, through a novel framework called MathGen. MathGen consists of three primary components: a math problem encoder, a difficulty predictor, and a question generator. The math problem encoder utilizes a graph neural network, GNN, to represent mathematical expressions as graphs, capturing complex relationships between mathematical objects. The difficulty predictor employs a neural network to predict the difficulty of a given math problem, based on features extracted from the encoded graph representation. The question generator uses a combination of natural language processing, NLP, and mathematical reasoning to produce novel math questions. The authors propose a novel algorithm, MathGen-Search, which leverages the difficulty predictor to guide the search for challenging math problems. MathGen-Search efficiently explores the vast space of possible math problems, identifying those that are both challenging and relevant. The paper presents a comprehensive evaluation of MathGen, using a dataset of over 10,000 math problems. The results demonstrate that MathGen can generate math questions that outperform existing state-of-the-art systems in terms of difficulty and relevance. The authors provide an analysis of the generated questions, highlighting the diversity and complexity of the problems produced by MathGen. While MathGen shows promise, the authors acknowledge limitations, including reliance on a large dataset of math problems, which may not be readily available for all domains. Further evaluation and refinement of the MathGen framework are necessary to ensure its effectiveness in real-world educational settings. Despite these limitations, the AI-assisted generation of difficult math questions paper presents a significant contribution to the field of math education, demonstrating the potential of AI and machine learning to generate challenging and relevant math problems. The paper addresses the challenges in generating high-quality, diverse, and difficult math questions for evaluating large language models, LLMs. It highlights the dichotomy between human-generated questions, which are of high quality but not scalable, and LLM-generated questions, which are scalable but often lack the necessary difficulty and diversity. The authors propose an AI-assisted framework for generating difficult math questions by leveraging the understanding of mathematical skills possessed by top LLMs. This approach involves extracting core skills from existing datasets, such as the math dataset, and using these skills to generate novel questions that test a wide range of abilities. The generated questions are then reviewed and corrected by human annotators to ensure their quality and relevance. The paper also touches on the issue of evaluation saturation phenomenon, where LLM evaluations become saturated due to across-the-board improvements and evaluation-specific enhancements. Overall, the proposed framework aims to create a more robust and challenging evaluation dataset for LLMs, ultimately leading to better models that can handle complex mathematical problems. A novel AI-assisted pipeline is presented for generating high-quality questions that require the application of multiple skills. The pipeline consists of 5 stages: skill pair validation, question generation, attempted solution, question validation, and final solution. Initially, the model validates a pair of skills to ensure they are distinct and not too similar. Then, it generates a question that necessitates the application of both skills for its solution. The model attempts a solution to the generated question, and the question is validated based on the attempted solution, checking for correctness, skill rigor, clarity, and other quality criteria. Finally, valid questions are resolved by the model using advanced techniques to enhance the accuracy of the final solution. The use of random pairs of skills drives improved diversity and difficulty among generated questions, requiring out-of-distribution thinking. This approach combines skills from 2 subareas, such as linking area and perimeter calculations with prime number knowledge. The resulting questions are challenging for both language models and human raters, and the new dataset, MATH2, is significantly harder than the existing math dataset. Human experts play a crucial role in the AI-assisted process, refining generated questions to enhance their engagement value and providing gold standard answers. This collaboration boosts human productivity and results in high-quality, novel questions distinct from those in existing datasets. The concept of scalable oversight is also discussed, highlighting the need for humans to supervise and check AI systems that potentially outperform humans in many relevant skills. The AI-assisted pipeline is illustrated in Figure 1, and examples of generated questions demonstrate the effectiveness of the approach. The methodology has the potential to introduce fresh perspectives into math instruction for AI and human learners, and the resulting dataset, MathGen-2, is a valuable resource for evaluating the performance of language models in math-related tasks. The development of a new dataset, MathGen-2, is presented for evaluating the performance of large language models, LLMs, in solving complex mathematical problems. A structured approach combines the capabilities of LLMs and human expertise to generate challenging mathematics questions. The pipeline consists of skill extraction, question generation, and screening and validation steps. The authors compare the zero-shot chain of thought, COT, performance of various models on Math and Math2 datasets. Notably, proprietary models exhibit the smallest decrease in performance, while smaller models within the same family experience more significant performance drops. The relationship between Math and Math2 scores is also explored, revealing that Math2 questions are more useful than Math questions when used as in-context exemplars for various LLMs. The methodology for generating Math2 questions involves identifying and cataloging distinct mathematical skills from a dataset. Questions are generated by combining pairs of distinct skills to increase their difficulty. A rigorous screening and validation process filters out invalid or flawed questions, ensuring the accuracy and quality of the generated questions and their solutions. This process provides a robust and comprehensive evaluation of mathematical skills. The Math2 dataset sheds light on interesting behaviors and failure modes of leading LLMs observed during the question generation process. The dataset's design and construction enable a nuanced understanding of LLM's strengths and weaknesses in solving complex mathematical problems. By leveraging human expertise and LLM capabilities, the Math2 dataset offers a valuable resource for evaluating and improving the performance of LLMs in mathematical problem-solving. The paper introduces a 5-step approach to generate challenging math questions using advanced models. This process is motivated by the difficulties in creating high-quality, novel math questions that require the application of multiple skills. The approach employs a large language model, LLM, to validate skill pairs, generate questions, attempt solutions, validate questions against a fixed rubric, and obtain final solutions. Step 1 involves validating the skill pair by assessing qualitative similarity between two skills. Reference examples from the math dataset are provided in context to enrich the model's understanding of the skills. If the skills are deemed too similar, they are flagged and excluded from question generation. In Step 2, the LLM is prompted to generate a question and a brief solution requiring the application of both skills in the sampled pair. The question must either require an exact answer or specify that an approximate answer is acceptable, and it should ask for only a single final result. In context, multi-turn conversations between a human and an AI assistant are provided to demonstrate the human providing feedback on the AI-generated questions, which the AI then refines. Step 3 involves the model attempting a solution to the generated question, adopting an adversarial approach to identify flaws such as insufficient information, ambiguity, self-contradiction, or excessive computation. If any issues are found, the model stops solving and clearly states the problems. Otherwise, it completes the solution. In Step 4, the generated question and its solution are validated against a fixed rubric consisting of 7 criteria: single answer requirement, exact answer requirement, dual answer requirement, clarity and completeness, computational tractability, realism and logic, and syntax and grammar. The model uses reference examples and validation exemplars to facilitate this step, employing majority voting, MAJ at 4, to enhance robustness. Step 5 involves asking the LLM to resolve the question to obtain a final solution, providing reference examples in context to improve the model's understanding. Majority voting, MAJ at 4, is used to ensure consistency. If all the answers obtained in this step are unique, indicating potential ambiguity, the question is discarded. The questions obtained from the above pipeline are further screened by humans, demonstrating the difficulty and quality of the math too, while also analyzing the behavior of different models on this task of compositional generalization. The paper evaluates a wide range of models spanning a large range of parameter counts on Math 2 and compares against their performance on Math, which is the base dataset. The Math 2 dataset is a challenging extension of the Math dataset, comprising 180 question solution pairs that have undergone human verification and modification to increase difficulty and quality. A total of 79 examples, 43.89%, were modified, with 41 questions and 62 solutions altered to improve clarity, correctness, or interest. The modifications were categorized into minor and significant changes, with 14 significant modifications making the questions harder or correcting them. The experimental setup follows the pipeline proposed by Didolkar et al. 2024, to extract skills from the math dataset, which encompasses 7 high-level topics. The skill extraction process identifies 114 skills, and after removing simple skills, the remaining set is used to generate questions using the proposed approach. The generated questions are then verified and modified to create the Math 2 dataset. The distribution of skills in MATH2 is shown in Figure 5, which is not included in this summary. The dataset is then used to evaluate the performance of various language models, including GPT-4 Omni, Claude 3.5 Sonnet, GPT-4 Turbo, and others. Table 2 presents the comparison of zero-shot COT performance, accuracy, on the generated dataset versus the math test set. The results show that GPT-4 Omni demonstrates the least drop in percentage terms, 13.42%, while Mammoth 7B shows the highest relative drop, 92.91%. The evaluation of language models on Math 2 reveals significant performance drops compared to the math test set, indicating that MATH2 is a more challenging dataset. The results suggest that MATH2 is a valuable resource for evaluating the performance of language models on math-related tasks. The dataset's difficulty and quality are attributed to the human verification and modification process, which ensures that the questions are more challenging and interesting for humans. The authors assess the performance of several large language models, including GPT-4 Omni, GPT-4 Turbo, Gemini 1.5 Pro, Claude 3.5 Sonnet, and Claude 3 Opus, on 2 datasets, Math and MATH2. MATH2 is a generated dataset that combines skills from different subareas of math, making it out of distribution, OOD, compared to the original math dataset. The results show that all tested models have significantly lower performance on Math 2 than on Math, with percentage drops ranging from 13.42% to 35.45% for frontier models. The authors initially attribute the performance drop to the OOD nature of MATH2, suggesting that it measures a model's OOD resilience. However, upon plotting the performance on Math 2, y, against the square of the performance on Math, x2, they discover a linear relationship, y approximately equals x2. This implies that the relative drop in performance is predictable from a model's performance on Math alone, without considering its training details. The authors propose a heuristic explanation for this relationship, assuming that a model's performance on Math reflects the average success rate of applying individual skills. On a random question requiring 2 skills, the probability of correct answering should be proportional to the product of the success rates of those skills. This would result in a quadratic relationship between the performance on Math and MATH2. The findings suggest that the performance drop on MATH2 is not solely due to OOD issues but rather an inherent property of the model's skill composition. The authors also note that open-source models, such as MetaMath and Mammoth, exhibit larger performance drops, likely due to overfitting to synthetic training data. In contrast, proprietary models of similar size show a more consistent pattern, with the relative drop in performance being predictable from their math performance. The evaluation uses the Mammoth evaluation suite for response generation, with a GPT-4 grader checking the correctness of solution responses against ground truth solutions. The temperature is set to 0, and top_p is set to 1 for all models. Additional details on compute resources and best fit quadratic curves are provided in Appendix A.3. The paper introduces a new dataset, MathGen-2, designed to assess the ability of AI models to apply multiple skills in solving math problems. The authors employ a pipeline involving prompting a large language model with a skill and topic, followed by validation of the generated question and solution. They find that model performance on Math2 is lower than on the original math dataset, indicating that Math2 questions are more challenging and require the application of multiple skills. The authors also explore the relationship between the number of skills required for a question and model performance. As the number of skills required increases, model performance decreases, suggesting that Math2 questions genuinely require the application of multiple distinct skills. Additionally, the authors test the quality of generated questions by using them as in-context exemplars for the math dataset. They find that Math2 questions serve as effective in-context exemplars, leading to improved performance on the math test set. The paper also discusses some failure modes of the question generation pipeline and highlights the importance of human raters in improving the generated questions. It notes intriguing behaviors of the models where they successfully create interesting and creative questions. The performance of various models on the math dataset under different prompting strategies is discussed in this section. 4 methods are compared: Mammoth 4-shot caught, skill-based 4-shot caught, proposed 4-shot caught, and proposed plus skill-based 4-shot caught. The proposed 4-shot caught strategy consistently outperforms vanilla few-shot prompting, with gains of up to 3.75% for Mixtral 8x7b instruct. Examples of creative questions generated by the models are provided, which often require human intervention to verify their validity and correctness. These examples illustrate the challenges in generating math problems that are difficult for automated tools but solvable by humans. Human raters play a crucial role in refining these questions to ensure they employ the intended math skills and are of high quality, readability, and difficulty. In the realm of advanced mathematical problem solving, large language models, LLMs, have shown potential in generating complex questions. However, these models often exhibit several failure modes that can significantly impact the quality and relevance of these questions. This includes insufficient involvement of skills, insufficient information, unsolvable or computationally intractable questions, nonsensical questions, deceitful solutions, and finding a needle in the haystack. To address these issues, human oversight plays a crucial role in refining and improving the generated mathematics questions. By intervening at key points, humans can ensure that the questions are not only challenging but also creative and suitable for advanced problem solving. For instance, original questions may lack clarity or relevance, which can be rectified through human intervention. Examples of original and modified questions demonstrate the significant enhancement in quality and relevance achieved through human oversight. These modifications not only improve the comprehensibility of the questions but also make them more challenging and engaging for advanced mathematical problem solvers. The importance of human intervention cannot be overstated, as it bridges the gap between the potential of LLMs and the actual needs of advanced mathematical problem solving. By combining the capabilities of LLMs with the discerning eye of human oversight, we can create a more effective and efficient system for generating high-quality mathematics questions. The authors have developed a novel pipeline that leverages named skills from the math dataset and multi-turn interactions with advanced LLMs to generate math questions combining pairs of skills. These questions were reviewed and refined by human raters, resulting in a new math evaluation dataset, MathGen-2, which is significantly more challenging for leading models. The proposed framework produced questions with greater novelty and difficulty compared to those in the original math dataset. The authors demonstrated that providing the newly generated questions as in-context examples improved GPT-4o's performance on the math dataset more effectively than examples sourced directly from the math dataset. This finding further validates the quality of the questions produced by the proposed pipeline. Open-source models performed disappointingly on these new questions, suggesting that their performance should be improvable using novel questions of only moderate difficulty which the proposed pipeline can generate at scale. The authors plan to release detailed information about their pipeline to encourage further research and development in the field of open-source math models. They also discuss limitations in future work, including optimizing prompting strategies to produce higher quality questions initially, reducing human verification through the development of automated validation tools, and enhancing the pipeline by integrating a training-based feedback loop. Recent advancements in large language models, LLMs, have led to significant breakthroughs in synthetic data creation, mathematical problem-solving, and multimodal understanding. Notably, Chan et al. 2024 have scaled synthetic data creation to 1 billion personas, while Chowdhury et al. 2023 have developed the PaLM model, achieving state-of-the-art results in various natural language processing tasks. LLMs have also demonstrated metacognitive capabilities in mathematical problem-solving, as explored by Didolkar et al. 2024. This research highlights the potential of LLMs to reason mathematically and solve complex problems, extending their capabilities beyond traditional language processing tasks. For instance, LLMs can learn to recognize and apply mathematical concepts, such as algebraic manipulations and geometric transformations, to solve problems. Targeted data generation with large language models, proposed by Gupta et al. 2023, aims to generate high-quality synthetic data for various purposes, including training and fine-tuning LLMs. This approach has significant implications for improving the performance and robustness of LLMs. The math dataset, introduced by Hendricks et al. 2021, is designed to measure mathematical problem-solving abilities of LLMs, providing a benchmark for evaluating their performance. Furthermore, researchers have explored the use of unnatural instructions for tuning language models, as described by Honovich et al. 2022, and keypoint-driven data synthesis for enhancing mathematical reasoning, proposed by Huang et al. 2024. These approaches have shown promise in improving the mathematical problem-solving capabilities of LLMs. The development of LLMs has significant implications for various applications, including education, scientific research, and natural language processing. As LLMs continue to evolve, it is essential to investigate their limitations, assumptions, and potential biases to ensure their responsible development and deployment. Future work should focus on addressing these challenges and exploring new applications of LLMs in various domains. In this section, the authors delve into the intricacies of the question generation pipeline, providing supplementary experimental details and results. They discuss various failure modes of the models during the question generation process, such as insufficient involvement of skills, where models generate questions that either miss one of the skills completely or require a shallow application of one skill while the other is sufficiently involved. This leads to potentially easy questions, defeating the purpose of skill composition. The authors also highlight interesting behaviors exhibited by the models throughout the pipeline, including creative questions generated by the models. For instance, when asked to combine the skills ratio _and proportion in geometry, Claude Opus generated a question that, although mathematically correct, did not require a rigorous application of both skills. The appendix also provides details about the compute used for running the experiments, as well as further analysis of the model evaluations. The authors discuss the different considerations that human annotators were instructed to take into account while annotating and verifying the questions generated by the proposed pipeline. Furthermore, the appendix includes examples of questions generated by different models in the question generation step, as well as a detailed description of the prompts used for each step in the question generation pipeline. The authors also provide a link to the skill exemplar repository and in-context exemplars used in the question generation process. The author's analysis of the failure modes and interesting behaviors of the models provides valuable insights into the limitations and potential areas of improvement for the question generation pipeline. The additional experimental details and results offer a more comprehensive understanding of the pipeline's performance and the challenges associated with generating high-quality questions that require a rigorous application of multiple skills. The authors of the research paper discuss common failure modes of their question generation pipeline, which aims to create math problems that combine multiple skills. One issue is the lack of involvement of certain skills, such as ratio and proportions, in generated questions. To address this, the authors employ multi-turn human-AI interactions to prompt the model to generate questions that combine skills in a more meaningful way. They also modify the question validation step to ensure that the complexity of each skill application in the question is similar to or greater than the complexity of the skills in reference examples. Another issue is the generation of questions with insufficient information or details essential for solving the problem. For instance, a question about installing a streetlight may lack details about the inclinations and elevations of the paths relative to the streetlight's position. To screen such questions, the authors include an explicit clause in the question validation prompt and also use a solution attempt step to detect missing information. The authors also discuss the generation of unsolvable or computationally intractable questions. For example, a question about a rectangle with an area of 360 square units and sides belonging to two arithmetic progressions may have no solution that satisfies all constraints. Similarly, a question about an infinite series of numbers may require manually calculating a large number of terms to find the sum. These types of questions are problematic because they are either impossible to solve or require an unreasonable amount of computation. To address these issues, the authors propose modifications to their question generation pipeline, including the use of multi-turn human-AI interactions, explicit clauses in the question validation prompt, and solution attempt steps to detect errors. These modifications aim to improve the quality of generated questions and reduce the occurrence of failure modes. The author's discussion of these failure modes and proposed modifications is connected to previous pages, which likely discussed the design and implementation of the question generation pipeline. The authors assume a high level of technical expertise in mathematics and computer science, and use domain-specific terminology and notation throughout the discussion. Examples of generated questions that illustrate the failure modes discussed include questions about a square garden, a streetlight, and an infinite series of numbers. The authors' proposed modifications to the pipeline aim to improve the quality of generated questions and reduce the occurrence of failure modes, ultimately leading to more effective math problem generation. Evaluating the reasoning abilities of large language models, LLMs, using math problems poses significant challenges. Three types of problematic questions can arise: those requiring brute force calculations, nonsensical questions, and deceitful solutions. Questions that necessitate brute force calculations, such as finding the sum of digits of a large number, are not ideal for assessing reasoning abilities. These questions can be solved through computational power rather than reasoning, and may be bottlenecked by the model's context length. To address this, a condition is added to check for computational tractability and solvability in the verification prompt. Nonsensical questions, which are confusing, incomprehensible, logically inconsistent, or ambiguous, also pose a challenge. For instance, a question that is logically inconsistent, such as a square plot of land fitting inside a quarter circle, can be filtered out through checks in the question validation prompt. Additionally, uniqueness of answers is verified in the final solution step. Deceitful solutions, where the model fabricates solutions to nonsensical or unsolvable questions, are another concern. For example, a question with no solutions may prompt the model to argue for alternative solutions. To mitigate this, solutions generated in the question generation prompt are not used, and a final solution step is added, where the model is asked to solve the question again. To ensure robust question validation, a sophisticated 15-step prompt is designed to catch various failure modes and guarantee that generated questions are valid and solvable. This approach underscores the importance of carefully designing evaluation methods for LLMs to accurately assess reasoning abilities. By filtering out problematic questions and deceitful solutions, a more robust evaluation framework for LLMs can be established. The validation prompt for the dual skill requirement consists of three components: skill descriptions with 3 exemplars for each of the 2 skills, 6 long validation exemplars, and the rest of the prompt comprising the 7 conditions described in Section 2. Initially, the names of the 2 skills to be combined were mentioned only once throughout the prompt, leading to model confusion between the pair of skills at hand and skills mentioned in the validation exemplars. The model also failed to locate the original skill names, instead generating its own skill names based on the skill exemplars provided. To address this issue, referential terms such as above given skills and these skills were replaced with the actual skill names, significantly reducing the problem. An example of the phenomenon is provided, where the model checks the question for the presence of unrelated skills in the reasoning trace. The corrected prompt ensures that the model accurately identifies the pair of skills to be combined. The reasoning trace of the model evaluates the given question and solution against the specified criteria, including single answer requirement, exact answer requirement, dual skill requirement, clarity and completeness, relevancy of information, and realism and logic. The solution demonstrates a rigorous application of both skills, using probability calculations and number-theoretic concepts to arrive at the final answer. The model's evaluation of the question against the dual skill requirement criterion is notable, as it checks for the presence of two distinct mathematical skills: probability theory and number theory. The solution's complexity is on par with the provided examples, and the model correctly identifies the skills required to solve the problem. The corrected prompt and the model's evaluation of the question against the specified criteria demonstrate the importance of precise language and accurate skill identification in the validation prompt. The use of actual skill names instead of referential terms significantly improves the model's performance, allowing it to accurately identify the pair of skills to be combined and evaluate the question against the specified criteria. The evaluation of a question validation model's performance in identifying and addressing various failure modes is crucial for ensuring the accuracy and reliability of the generated questions. Syntax and grammar play a significant role in this process, as they help to eliminate potential errors that could lead to invalid or nonsensical queries. In addition to these fundamental aspects, human verification is essential for double-checking the validity of both the questions and their corresponding solutions. This step not only improves the readability, quality, and difficulty of the content but also helps to refine it based on practical considerations such as computational tractability and geometric feasibility. Moreover, the models have been observed to exhibit creative behaviors during the validation process. For instance, they consider factors like computational efficiency and practical geometry when generating and validating questions. This demonstrates their ability to adapt and learn from complex datasets and real-world scenarios. Overall, the interplay between machine learning models and human annotators is critical for producing high-quality, valid questions that can effectively assess a student's knowledge and understanding of a subject matter. By leveraging the strengths of both artificial intelligence and human intuition, educators can create more effective and engaging learning materials that cater to diverse learning styles and abilities. Analyzing the performance of various models on Math and Math2 datasets reveals a quadratic relationship between the two. Specifically, the performance on MATH2, which requires two skills at a time, follows the quadratic relation y equals 0.0166 minus 0.0776x plus 1.096x2. This indicates that as the complexity of the questions increases, the model's performance degrades. Notably, smaller models exhibit larger degradation in performance compared to their larger counterparts, with the exception of the GEMMA family of models. For instance, the 7B parameter model shows a 66.669% deterioration, whereas the 2B parameter model shows a 63.03% deterioration. The page also showcases examples of original and modified questions, demonstrating how human annotators reworded the questions to eliminate brute force computation and encourage more analytical thinking. By rephrasing questions, human annotators can force models to adopt a more analytical approach. For example, an original question requiring simple computation was modified to require understanding the underlying pattern. Another question was rephrased to avoid enumeration, promoting a more analytical approach. These findings emphasize the importance of understanding the limitations and strengths of different models when dealing with complex mathematical problems. Human intervention plays a crucial role in refining questions to better assess the model's capabilities. By acknowledging the quadratic relationship between Math and Math2 performance, researchers can develop more effective strategies for improving model performance on complex mathematical tasks. The authors conduct an in-depth analysis of performance degradation on smaller models and skill representation in the generated dataset, utilizing open-source large language models, LLMs, and commercial models, including GPT-4 Omni, GPT-4 Turbo, and Claude 3 Opus. The evaluation is performed on a generated set of questions, revealing that smaller models experience larger relative performance declines compared to larger models in the same family. This phenomenon aligns with previous findings on compositional generalization, suggesting that larger models are better at composing skills or concepts than smaller models. The skill representation in the generated dataset is analyzed, revealing a non-uniform distribution of skills. The authors extract 97 skills out of 114 skills via the skill extraction process, with each question representing 2 skills. The distribution of skills is visualized in Figure 5, showing that multiple skills are represented by only one question. The authors investigate the skill composition using different models by prompting them to generate a question combining 2 different skills: area calculation skills and algebraic manipulation skills. The responses of each model, including GPT-4 Omni, Claude 3 Opus, Gemini 1.5 Pro, and Llama 370B Instruct and Llama 38B Instruct, demonstrate their ability to combine different skills and generate a question that requires both skills to be solved. For example, GPT-4 Omni generates a question that tests both area calculation skills and algebraic manipulation skills, involving a rectangle and a right triangle. The experimental setup for evaluating the models includes the use of 280 GB A100 GPUs and 72 GB of RAM for open-source LLMs, and 25 parallel workers for making API calls to commercial models. The results of the experiments provide insights into the performance of different models on the generated dataset and the skill representation in the dataset. The analysis of performance degradation on smaller models and the skill representation in the generated dataset contribute to a deeper understanding of the strengths and limitations of different models. The examples of skill composition using different models demonstrate the ability of these models to combine different skills and generate questions that require multiple skills to be solved. Calculating the area of a triangle within a rectangle involves understanding the relationship between the areas of geometric shapes and applying mathematical formulas. Given a rectangle ABCD with area AB, the area of triangle PQR is 1/6 of this, or AB, 6. The vertices of triangle PQR are P, 0, 0, Q, A, KB, and R, Ka, B. Using the formula for the area of a triangle with vertices at x1, y1, x2, y2, and x3, y3, which is area equals 1/2 x1, y2, y3, plus x2, y3, y1, plus x3, y1, y2, we can substitute the coordinates of P, Q, and R into the formula to find the area of triangle PQR. This results in the equation area of PQR equals AB, 2, 1K. Since we know that the area of triangle PQR is AB, 6, we can set up the equation AB, 2, 1K, equals AB, 6. Solving for K, we find that there are 2 possible values for K: 2/3 and 4/3. This solution demonstrates the application of mathematical formulas to solve for unknown variables in geometric problems. In this challenging problem, students are required to utilize both area calculation skills and algebraic manipulation skills. The task involves an equilateral triangle ABC with a side length of 2a, and points D, E, F as the midpoints of sides BC, CA, AB respectively. The objective is to express the area of the shaded region, consisting of the equilateral triangle DEF and squares ACDE, ABFG, BCHI, in the form Ka2, where K is a constant, and then find the value of K. The solution begins by calculating the area of equilateral triangle ABC as square root 3a2. Then, the side length of equilateral triangle DEF is determined as square root 3a. The area of DEF is calculated as 3 square root 3/4 a2. Each square has a side length of 2a, so their combined area is 12a2. Adding these together gives the total area of the shaded region as 12 plus 3 square root 3/4, A2, with k approximately equals 15.1981. This question effectively tests students' understanding of geometric calculations and algebraic manipulation, while providing an interesting visual representation through the equilateral triangle and square constructions. The solution is straightforward to evaluate, making it suitable for assessing student comprehension. This research explores two geometric problems that require algebraic manipulations to solve. The first problem involves finding the area of a smaller circle inscribed within an equilateral triangle. By establishing the relationship between the radii of the larger and smaller circles using the centroid of the equilateral triangle, a quadratic equation is derived to solve for the radius of the smaller circle. Applying the Pythagorean theorem to right triangle POC yields the equation r squared plus r2 squared equals s2 squared, where r is the radius of the smaller circle and s is the side length of the equilateral triangle. Solving this equation using the quadratic formula yields the value of r, and subsequently, the area of the smaller circle is calculated using the formula pi r squared. The second problem requires finding the area of a shaded region within a square inscribed in a circle. The solution involves calculating the area of the square and subtracting the area of a semicircle inscribed within the square. The area of the semicircle is determined using the formula 1/2 pi r squared, where r is the radius of the semicircle. By analyzing the geometric configuration, the radius of the semicircle is found to be 2, and the area of the semicircle is calculated as 2 pi. The area of the shaded region is then obtained by subtracting the area of the semicircle from the area of the square. Key concepts and methodologies employed in these problems include geometric calculations, such as finding the area of circles, semicircles, and squares, as well as algebraic manipulations, including solving quadratic equations with radicals. The Pythagorean theorem and quadratic formula are also applied to derive and solve equations. The solutions demonstrate the importance of algebraic manipulation skills and attention to detail in mathematical problem-solving. Visual aids, such as figures and graphs, are used to illustrate the geometric configurations and facilitate understanding of the problems. The step-by-step solutions provide clear explanations and justifications for each mathematical operation, highlighting the application of mathematical concepts to solve geometric problems. The page discusses a complex mathematical problem involving the calculation of the area of a region bounded by a curve and the z-axis. The curve in question is y equals x squared 4x plus 3, and the region of interest is between x equals 0 and x equals 2. To solve this problem, we need to integrate the function with respect to x, which results in an expression that simplifies to 2 square units when evaluated from x equals 0 to x equals 2. This problem tests both area calculation skills and algebraic manipulation skills, as it requires the student to find the area of a region bounded by a curve and the z-axis, and also to integrate a function with respect to x. The answer is not a simple numerical value, but rather an expression involving pi, adding an extra layer of complexity to the question. Generating a mathematical question that tests both skills, less than skill underscore 1 greater than and less than skill underscore 2 greater than, requires expertise in both areas to be solved. To create such a question, a detailed explanation of the skills is necessary. Less than skill underscore 1 greater than and less than skill underscore 2 greater than are described through a series of questions and answers, providing insight into the skills requirements. For instance, less than skill underscore 1 greater than is demonstrated through questions such as less than skill underscore 1 underscore question underscore 1 greater than and less than skill underscore 1 underscore question underscore 2 greater than, with corresponding answers less than skill underscore 1 underscore solution underscore 1 greater than and less than skill underscore 1 underscore solution underscore 2 greater than. Similarly, less than skill underscore 2 greater than is exemplified through questions less than skill underscore 2 underscore question underscore 1 greater than, less than skill underscore 2 underscore question underscore 2 greater than, and less than skill underscore 2 underscore question underscore 3 greater than, with answers less than skill underscore 2 underscore solution underscore 1 greater than, less than skill underscore 2 underscore solution underscore 2 greater than, and less than skill underscore 2 underscore solution underscore 3 greater than, respectively. Upon examination, it becomes apparent that the skills are not identical. While both involve mathematical reasoning, they require distinct approaches and problem-solving strategies. For example, less than skill _1 greater than focuses on algebraic manipulations, whereas less than skill _2 greater than involves geometric reasoning. Given the distinct nature of the skills, a question can be generated that tests both skills. The prompt for question generation is, create a challenging math question that tests both skills, less than skill _1 greater than, less than skill _2 greater than, and provide a brief solution. The generated question and solution are as follows. What is the value of x in the equation 2x plus 5 equals 11, given that the equation represents the relationship between the perimeter of a rectangle and its length? X equals 3. This question requires the application of both less than skill _1 greater than and less than skill _2 greater than. The student must first use algebraic manipulations to solve for x, and then use geometric reasoning to understand the relationship between the perimeter and length of the rectangle. The complexity and difficulty of the skills in the generated question are similar to those in the example questions. The question is designed to be challenging yet solvable, with a clear and concise solution. Evaluating a student's analytical and mathematical reasoning abilities in a math exam requires a nuanced approach. Two specific mathematical skills, spatial reasoning and algebraic manipulation, are crucial for solving complex problems that demand expertise in both areas. The evaluation process is designed to assess students' ability to apply these skills simultaneously without relying on computational devices. A conversation between two agents, Agent A and Agent B, highlights the importance of clear communication in mathematical problem-solving. Agent A presents a problem, and Agent B responds with a solution, demonstrating the need for precise language and unambiguous instructions. However, an attempted solution to a question intended to test analytical and mathematical reasoning abilities reveals potential flaws in the question's design. The solution takes a defeatist approach, suggesting that the question may be unsolvable, self-contradictory, computationally intractable, ambiguous, or open to multiple interpretations. This underscores the need for rigorous question validation to ensure that assessments accurately measure student skills. Effective question validation requires precise and clear language, avoiding ambiguity and the need for approximations. Consistent naming of skills is also essential to prevent the lost in the middle problem, where students become confused due to inconsistent terminology. By emphasizing these best practices, educators can create assessments that accurately evaluate students' analytical and mathematical reasoning abilities, providing a more comprehensive understanding of their skills. Evaluating questions for assessing students' skills in simultaneous application of two skills, less than skill _1 greater than and less than skill _2 greater than requires careful review of the question's quality and suitability. To ensure high-quality questions, several criteria must be met. Firstly, the question should have a single answer requirement, meaning it should ask for one and only one final result, without requesting multiple distinct answers or pieces of information. Additionally, the question should meet the exact answer requirement, where it is possible to achieve one exact answer without making approximations or assumptions, unless explicitly specified. The question must also satisfy the dual skill requirement, which necessitates rigorous expertise in both less than skill _1 greater than and less than skill _2 greater than for resolution. The application of both skills and their subskills should be necessary and contribute directly to obtaining the final answer. Furthermore, the question should demonstrate clarity and completeness, being unambiguous and containing all necessary information to complete the solution. Any required assumptions not common knowledge should be explicitly stated. Computational tractability is another crucial criterion, as students are expected to solve the questions within a given time limit without access to computational devices. The question should be computationally tractable, and all computations involved can be done by hand in a limited amount of time. The relevancy of information criterion ensures that the question does not have any extra details that do not contribute to solving the problem. The question should also demonstrate realism and logic, involving realistic scenarios or hypotheses with logically consistent data. The specified operations and contextual setup should reflect plausible mathematical situations. Finally, the question must be grammatically correct and clearly written to prevent misinterpretation, meeting the syntax and grammar criterion. To assess the question's quality, a thorough analysis of these criteria is necessary, along with consideration of any other relevant analytical points concerning mathematical reasoning and problem-solving. The assessment should be structured as follows: a detailed analysis justifying the decision, followed by a yes or no answer indicating whether the question is high quality and suitable for evaluating the students. The evaluation process involves reviewing the combination of skills intended for assessment, checking the logical flow and mathematical correctness from the question's setup to the solution's conclusion, and accounting for potential pitfalls such as logical inconsistencies, unnecessary complexity, or insufficient detail. Example question-answer pairs for the two skills are provided to facilitate understanding, along with sample conversations between an AI agent and a teacher to illustrate potential difficulties in this task. This page presents a series of question-answer pairs and conversations to validate the effectiveness of a mathematical problem-solving approach. The content is structured around two distinct mathematical skills, each accompanied by 3 sample question-solution pairs. The first skill, denoted as Skill 1, encompasses 3 questions with corresponding solutions. Similarly, the second skill, Skill 2, also comprises 3 question-solution pairs. These question-answer pairs serve as exemplars to demonstrate the application of each mathematical skill. Following the presentation of these skills, 6 conversations are provided, labeled as Conversation 1 through Conversation 6. These conversations appear to be validation exemplars, possibly used to assess the model's ability to engage in mathematical discussions and provide accurate solutions. A question to be checked is then presented, accompanied by a solution attempt. However, the final solution deviates from the attempted solution and instead utilizes in-context exemplars from Hendricks et al., 2021. This approach is presented as the final solution, with a prompt that describes the 2 mathematical skills and their corresponding question-solution pairs. The final solution prompt is structured similarly to the initial presentation of the skills, with Skill 1 and Skill 2 each followed by 3 question-solution pairs. This suggests that the final solution approach relies on the same mathematical skills and exemplars as the initial presentation. The page concludes with a "Thank you very much" message, which may indicate the end of the validation process or the completion of the mathematical problem-solving task. Overall, this page appears to focus on the validation and demonstration of a mathematical problem-solving approach, using a combination of question-answer pairs, conversations, and in-context exemplars. Evaluating a student's math exam solution requires a step-by-step assessment of their thought process and problem-solving skills. A comprehensive evaluation involves comparing the student's solution to the correct solution, focusing on the application of mathematical concepts and the systematic approach taken to arrive at the answer. The problem presented involves applying algebra and geometry skills to solve a mathematical problem. The correct solution demonstrates a clear understanding of these concepts, applying them systematically to obtain the correct answer. To evaluate the student's solution, it is essential to understand the problem and the skills required to solve it. The student's solution should be compared to the correct solution, examining the steps taken and the final answer obtained. If the student's solution mirrors the correct solution in terms of the steps taken and the final answer, it can be concluded that the student has solved the question correctly. A correct solution involves a systematic approach, applying mathematical concepts such as algebra and geometry to arrive at the answer. The student's solution should demonstrate a clear understanding of these concepts and apply them correctly to obtain the correct answer. In evaluating the student's solution, it is crucial to consider the following key aspects. Does the student's solution demonstrate a clear understanding of the mathematical concepts required to solve the problem? Are the steps taken by the student systematic and logical, leading to the correct answer? Does the student's solution obtain the correct answer, and if not, what errors were made? By examining these aspects, it is possible to determine whether the student's solution matches the correct solution and assess their problem-solving skills and understanding of mathematical concepts.